Let's talk about periodic table trends based on Coulombic attraction. You may recall that Coulombic attraction is the attraction of plus charges for minus charges. The electron is negatively charged. The nucleus is positively charged. We're going to talk about the various trends we see in the periodic table that have to do with that plus to minus attraction. Now, how does the force on the valence electrons change? You'll recall that the valence electrons are the ones in the outer shell, or the outer energy level. As we move from top to bottom in a column, the distance between the outer shell electrons, the valence electrons, and the nucleus, that distance increases. The distance effect is very, very important. As we get closer, in fact, the shortened distance makes the force go up even faster than we expect. As we move from left to right in a period, what is happening is the nuclear charge is increasing by 1 every time we move to a different element. So we go, for instance, from boron element 5 to carbon element 6. We increase the percent of charge, so to speak. The overall charge of the nucleus increases by more than 10%, just moving one element. So as we move from top to bottom in a column, we expect the force to go down, and go down fairly dramatically, because the atom is getting bigger, and the valence electrons, the ones we would pull away in an ionization, they're getting farther and farther from the nucleus, kind of like Pluto from the Sun. And as we move from left to right in a period, since that nuclear charge is increasing, the tug, the force on the outer shell electrons is going to be increasing as well. So we expect, as we go from left to right in the periodic table, since the charge is increasing and the force is increasing going left to right, we would expect that the outer shell electrons will be pulled closer and closer to the nucleus. And indeed that is true. So opposite, as we go from right to left, we expect the atomic radius to be going up, and it does. And as we go from top to bottom, of course, we're increasing the number of shells. We are increasing the distance between the outer shell electrons and the nucleus. The atomic radius should go up as we go from top to bottom, and indeed it does. Pauling electronegativity. Dr. Pauling based his electronegativity table on the highest electronegativity being fluorine. Electronegativity really refers to the amount of tug that the outer shell electrons feel, and the amount of tug that a new electron feels from the nucleus as it's pulled in. That's particularly going to happen with nonmetals. So this is a table showing the electronegativities according to Dr. Pauling's scale. Going here, you'll see that cesium, which is very, very large and is also a group 1 element, cesium has the smallest electronegativity shown, 0.7. Fluorine, which is very small and has the most electrons of an active element in that second column, fluorine has the highest electronegativity of 4. Oxygen is next to that. Nitrogen is next to that. These are the 3 most highly electronegative elements on the periodic table, and that will become very, very important later when we study bond polarity. As you see, as you go from right to left on the table, it's almost like a stair step. The fluorine, of course, is very high, and the lithium is very low. And as we go from top to bottom in each of these columns, the electronegativity is going down. Same thing in column 2. the beryllium is going down to the barium of 0.9. Now, remember that hydrogen is not a metal, and so the fact that it has an electronegativity very close to that of boron and carbon is not surprising. Hydrogen does not tend to give away its electrons like the group 1 elements. It tends to share electrons with a non-metal. So as you can see, as you go from top to bottom in a column, the electronegativity is going down. As you go from right to left in a column, the electronegativity is going down. With the transition of metals, you can see that there is a steady increase going from left to right, and then you get in the middle and it kind of levels off. That has to do with the structure of the transition metal d electrons, which are filling up as you go from left to right here. But in general, as you go from top to bottom, the electronegativity goes down. First ionization energy, as you can imagine, is definitely connected to the tug of the outer shell electrons by the nucleus. That's the energy needed to remove 1 mole of electrons from 1 mole of atoms. And as you can see, and as you can expect, as we get smaller and smaller atoms with more and more nuclear charge going left to right, the ionization energy is increasing. Moreover, as the distance between the outer shell electrons and the nucleus gets smaller, the ionization energy goes up, because again, the tug depends on distance. So ionization energy increases as you go up and as you go to the right. Ionization energy decreases as you go left and down. So the highest ionization energy would be in the nonmetals up here, also the highest electronegativity. The lowest ionization energy, as we already know, is going to be in the alkalis here, and that would also be highest at the top and lowest at the bottom. One thing you need to understand is what happens when an ion is formed. And what we have here are the radius of each atom and ion in picometers. The ions are colored red on the left, that looks orange to me, and blue on the right. And the parent atoms are brown. So you can see here, say with lithium, the parent atom, lithium atom, with no charge, is at 152, but the lithium ion is at 60. Why? Well, the lithium ion is formed by lithium losing its outer valence electron, losing that 1 electron, which we would know as a 2s electron. Beryllium 2+ is formed when the beryllium atom, the brown, loses 2 electrons to form the beryllium ion, which is orange. And again, that radius gets to be very, very small. On the other hand, when electrons are gained, as when nitrogen, neutral, 0 charge, gains 3 electrons, the ionic radius is much larger than the parent atom. Same thing with oxygen. You have oxygen atom here and the oxygen ion there. The oxygen ion is much larger than the oxygen atom. So, when metals become ions, they get smaller. When nonmetals become ions, they get larger. That's something, a general rule that you might want to remember as you move into a test.